And then, so I am going to share my screen and, okay, so I do want to remind you that we are having our second exam. It's a week from today, so it's as listed on the syllabus, and I have prepared like a PowerPoint that I'll post to Canvas later today. But I did want to kind of at least show you this, and again we'll start kind of going through the reminder that it is an in-person exam and that we have been scheduled in Todd Ware, the Todd Ware Auditorium, which is on the first floor of the CC building. So, and I'll remind you of that as we go. So just kind of an important thing to remember. And again, I don't really want to go through this in detail. We maybe can spend a little more time on Monday, but I do want to point out that it will cover through what we talk about on Monday. So I think we'll get through the thermoplastic and thermoset processing, but there may be a slight modification if needed. So it will pick up where we left off for the last exam. So there will be some on sheet metal, powder metallurgy, material removal processes. Oh, it says includes machining lab. Let's change that to homework, because oftentimes we do those calculations that we did in our homework for lab, and then the processing. So I really wanted to point out that you can bring in a sheet 8.5 by 11 with formulas, and then any other information that you feel would be helpful, but again, using one side of that 8.5 by 11 sheet. So there will not be any of the formulas given for machining. If there is data needed, like specific energy or number of cutting surfaces or like number of cutters, that would be given, but the formulas will not. Okay. So again, this particular PowerPoint, I mean, I like to have some level of detail so that you're aware of it. And again, I will post that probably when I get back to my office today. I want to kind of look over it one more time and make sure that I correct anything. So I just really wanted to give you a week's notice and just remind you of our exam next week, and especially to remind you that you'll be able to bring in a sheet. Okay, any questions on the exam? Okay. So let's go back to let's see which one this is. Okay, so let's go back to talking about thermoplastics. So, and not just thermoplastics, injection molding of thermoplastics. And I want you, if you can, to remember what was on the video clip that we saw yesterday. And again, when we think about some of the processing, thinking about the equipment, the tooling, and some of the various products that are made by injection molding. In lab next week, we are going to do a surface roughness experiment. So we're going to take those parts that were machined in a design of experiments and run the surface roughness. I also will have powder metallurgy parts, some machine parts, and plastic parts for you to look at. So we'll be able to look at some of these parts in detail. But again, injection molding of plastics, and really the basic process is what we saw. The starting material, again, for our thermoplastics, usually it's going to be as pellets or granulars. It's fed into a heated chamber. And we oftentimes see like it's either by hand, and in the video we saw somebody kind of pouring it in, or by a feeding system. And they start to melt. We often call the sort of the kind of the melted plastic a melt, and then we see that the melt is forced into a split die chamber to fill the part. So we have a gating system with this particular process, and then after cooling, the mold opens and the parts are ejected. So this is a very simple definition of the process, but it's basically what we have. The most common type of sort of feed mechanism is the reciprocating screw, and that was mentioned in the video as well. As our reading assignment indicated, you know, it's sort of like the plastic version of die casting. So this is for thermoplastics. For thermosets, so here we have a cooled mold for thermoplastics. So we have a hot plastic that we're forcing into a cold mold. If we injection mold thermosets, which we can, the mold is going to be heated, and then the parts are ejected when cured. So this would be sort of that final polymerization. So one of the things that we're going to be interested in is, for processes, can these processes do thermosets as well as thermoplastics? Injection molding is considered to be a process that can do both. Sometimes we do have a slightly different name for the process if we're doing thermosets. Okay. Now, let's get into some of the, again, this is going to be thermoplastic. So as we talk about these variables, we're really referring to thermoplastics. So let's kind of consider some of the various aspects. We want to understand, if we can, the variables, what we can control, and maybe a little bit on how part design factors in. Okay, so we've got some additional detail, but a couple things that we're going to be interested in. Pressure and clamping force, that's going to be related to how large of a machine you need. Probably is not a big surprise. The larger the machine, the higher the cost. And from yesterday's video, you can kind of, you know, have your mind around a little bit the systems that are needed as the machine gets larger. So we'll talk a little bit more of that. We're also going to be interested in a little bit on the flow of the material. So we want to kind of consider gate location, size of the gates, and we'll look more at some of these gates. One of the things that we do see is these are often very thin. One of the things that we do see with injection molding of plastics, and I have a couple examples of parts and pictures, is the gates are extremely small. Your book talks about how small a gate can be for a thin material. And if you remember in the video, oftentimes they were being cut off with just a simple tool. If you've had any injection molded parts that kind of come on the gating system, you often can just pull them off just with your hands. Location of the gates, you know, this is going to be to have sort of that nice thermal front. But we're not going to go into quite the detail on design for injection molding as we did with casting. So knit lines, this is where streams of plastic meet. So this can be around a hole, or it can be basically from multiple gates. Oftentimes there is a visual line on there. Not always, but it's something that this is really more involved with the how do we design the mold for the gates, the ejectors, and the cooling. Now, we are going to talk about cooling time. We recognize that cooling time is 50 to 70% of cycle time. And time is money. So if we want to have maximum efficiency, we want to reduce our cycle time, we want to have fast cooling time. And I think on our reading assignment, we had a little more information on that. Also, we'll look a little bit, and you could see the ejector pins. So injection molded materials are actually physically ejected from the machine by pins that sort of move and push the material out. The location of those ejector pins, generally they're going to be on the opposite side from the gates. So if we're feeding from one side of the part, usually we're going to eject from the other, and we cannot have a ejector pin at the same location as a cooling channel. So we cannot have an ejector pin at the same location. So most injection molding machines and dies do have cooling channels, so we're running water through it. So it allows the designer, the manufacturer, to control the cooling rate. We don't have Charbonneau's equation for injection molding, but that same concept does exist. So we oftentimes want to feed into the thicker area for the same reason we feed into the thicker area for a casting, but then we also have to consider where we're going to eject and where we might want to have a little bit more cooling. Okay, so here we're going to go into a little more detail in terms of the variables in injection molding. Some of the things that we can't control will be the viscosity of the polymer melt. Yesterday we talked about how viscosity changes with length of the polymer chains. So the higher the molecular weight, the degree of polymerization, the lower the viscosity. Also, the lower the temperature. We see lower temperature gives us, wait a minute, did I get that right? Large molecules raise the viscosity, lower temperatures raise the viscosity. Okay, so what we see is that the pressure needed increases as the viscosity increases. And this makes sense. So if we're at a lower temperature, we'll need a higher pressure because of the viscosity. If we have a plastic, like a high molecular weight polyethylene, we're going to need a higher pressure than if we were looking at a low density polyethylene, just because the high molecular weight is going to have longer chains. Okay. Also, the effective surface area of the part. So we have our clamping force increases as our surface area increases. And there's a formula in your book that says clamping force is pressure multiplied by effective surface area, and then you actually kind of increase that a little bit for the formation of flash if needed. But again, when we look at our a machine, so we realize that pressure and then clamping force are variables. So you're going to kind of put a note here. Pressure is often our limiting factor, although that certainly is going to be related to clamping force. Okay, and now part thickness, or essentially length over the diameter. So what we see is that the pressure increases as the thickness decreases. Well, and specifically we're looking at length over diameter. So we can decrease the length by increasing the number of gates. And so injection point. So essentially we are reducing that effective length. So that can decrease the pressure. We also realize though that cooling time decreases as thickness decreases. Okay. So a thicker part, lower pressure, so, oops. Here we go. So easier to inject, but slower cooling, which means longer cycle time. Okay. And so these are like, you know, for our quick perusal of injection molding, these are some of the big factors. And again, we see this trade-off between part thickness and cooling time, cycle time versus injection pressure. Now, we also, you know, and we also see that the viscosity of the polymer melt is also an important consideration. So a lot of this, again, goes back to some of those fundamentals of thermoplastics. Okay, so now let's look at some pictures. Again, as we consider this, just a kind of a simple overview. Here we have our hopper of our, you know, this is our thermoplastic. And it's going to kind of come down, and the screw is going to be rotating, and it's going to be moving or dragging the thermoplastic towards the die opening. There's going to be friction. We often have some external heating. We can talk about this as sort of drag flow. And this is probably the most common way to heat and move thermoplastics. We'll see this in some other processes as well, the reciprocating screw. And again, remember that the viscosity of a melted plastic is, we saw that yesterday sort of with that little bubble that was sort of slowly dropping down. We have that with the melt index. So we're never really that classic liquid like metal or water. But this is the most common way. And again, we're oftentimes feeding this thermoplastic, it's coming down, and then as it's moving in this direction, we're going to see the friction is going to start to heat it up. We may have some external heating, and by the time we're reasonably close to the actual dye, it's going to be sort of a cohesive liquid, and then it is just forced into, through a sprue, into the mold cavity. So let's look again. So here's an injection molding die set. So this is generally going to be made out of tool steel, although they can be made out of aluminum. There is a cost difference. There's also a kind of a longevity difference. If it's likely to be a large production run, then steel would be longer lasting. But again, we have the guide pins that just can make sure the halves come together. We have our mold cavity. Here we have those same words that we saw with casting. So we have our sprue, which is where the metal is, or excuse me, the plastic is injected. We have our runner, and then we gate into the mold cavity. And again, we have that words cavity and runner. So our features, you know, is going to be, again, very similar to die casting, but lower temperatures and pressure. So here is what would come out of a injection molding of 4 parts. So again, we have our sprue, we have our runner. We do have, this one shows that when we get to the actual gate into the part, it's relatively small. So we have that same, you know, kind of gating system that we would see in casting. This is not the best picture, at least it's not showing up on my screen as the best, but here's the part, here's the sprue, the branch runner, and we're gating. And then here we see the injector pins are coming out of the top mold, and they're forcing this down. So those ejector pins, and we did see that in the video as well. They sort of are like these fingers that come out and push the mold out. So this is one thing that often fascinates me is where we use what might be considered a negative as a positive. This happens to be a very old Happy Meal toy, and it was actually a little tabletop, like little hockey kind of toy. It was definitely made by injection molding, and what you can see down here is the little hockey sticks actually acted as the runners. And so the runners were incorporated into the process. And we see that there are gates. Each little net area has 4 gates, and we can kind of see it closer up here. And then we can also see at least the location of some of the ejector pins. And it's not uncommon that you will see that on an injection molded part. So one of the things that we often can look for on an injection molded part are evidence of the ejector pins, those circles. And we also sometimes can see, and I'm going to kind of back up to my first page, oops, we often sometimes can see the location of the gate itself, where it looks like there is a little bit of plastic kind of stuck out. Sometimes that's removed, sometimes it's not. If it doesn't affect the overall performance of the part, then it's just left there. But those are some things to look for to say, oh, was this made by injection molding? This is one, this I also think is kind of fun. It's a model of an injection mold made by injection molding. So here we have an example of the part, and here's the final part, and we have our little gate and sprue. So here we have our gate and sprue. Here we would have like the slide action, we have the ejector pin, and so forth. So this just amuses me a little bit, an example. So we also can do a core. If we core an injection molded part, just like if we had a die casting part, it's going to be a permanent feature and it's going to sort of slide in place and then come out. Obviously, that would increase the complexity and the cost. Here I also have some small parts with gating system. These parts on the left are actually that go on a Ziploc type bag, and this was they fell off the gating system no matter how careful I try. So here is the gating system for that. So each of these little parts are going to be on one of these trees. Here we have another set of parts. So here's a different gating system. So we have our, again, we're going to have our sprue in the gates, and we can see how it attaches there. I don't remember what these are little tips for something, but the evidence on the parts is that we can see the little gate area. Okay. So that just gives us some ideas of some injection molding parts. Now let's talk about the mold types. And again, this was gone over in the video, but we do talk about a 2-plate, a 3-plate, and a hot runner system. And what we're really talking about is by plate, this is how many features of the mold we have. So the simplest, so the lowest cost would be our 2-plate, and that is where the gating system remains attached to the parts. So this is our 2-plate. So we have plate 1, plate 2, our ejector pins, our sprue. So again, we're ejecting from the opposite side as the sprue, and the part and the gating system is removed. So we do have to physically remove the part from the gating system, but the mold costs are going to be lower because we only have the 2 plates. The next one is the 3-plate mold. So here we have the 3-plate. So we have this additional stripper plate. So we have the plate, ejector pins with our part. The gating system actually is separated from the part by the stripper plate, and then the feed plate, so to speak, is separate. So in the 3-plate, it's a more complicated mold because we have both the stripper plate and the part plate moving, but the gating system is separated from the part, so we don't have to have any additional labor to remove these. This particular 3-plate can be automated. And then the third one is our hot runner. And here we have the hot plate where the runners are always molten. That one I'm not as familiar with. I've seen more 2-plate and 3-plate, but in the hot runner system, the gating system is always going to be molten, and we're just sort of cycling it through. The nature of polymers are such that this is not really that big of a deal to have it. It's kind of just interesting. So again, our 3 mold types. And it's just indicated here. Okay, so let's see how we're doing. We're doing pretty good. So let's kind of talk about the characteristics of injection molding, and then we want to look at the features of the parts. So I'm going to start with, raise this table a little bit. I love. So injection molding still is, I'm going to change colors here. So it is the most widely used plastic process. Yes. So it is sort of the standard and so we compare other processes to injection molding. We have short cycle times. There is longer lead times. And this is to make the mold itself. So there are other processes that have shorter. Low labor costs. And for instance, the 3-plate mold can be automated. So in the video, we saw that, you know, we did see that in some of the machines, we did have workers who were removing the gating systems or pulling the parts out. But one worker can actually man quite a few injection molding machines. So it's not like you have to have one worker for one injection molding machines. If they're arranged in like a cell, they can actually kind of supervise multiple machines. And then the 3-plate mold, because the gating system is removed automatically, can have even lower labor costs. Now, we do have high tooling and equipment costs. And, you know, that just kind of means that we need to offset that cost by quantity. So again, just as die casting is not a good process for small quantity, injection molding has some issues with that as well. Residual stresses exist. And again, some of this is the temperature gradient. Most of it is that pressure gradient. So in thermoplastics, we see more residual stresses from a pressure gradient. And because we're injecting the material under pressure, we're not going to have uniform pressure throughout the material. And residual stresses can be an issue because there's something called environmental stress cracking, where if you have a material, and now for plastic that could be a solvent or it could be a material with that's more basic. So some detergents end up being more on the basic side. That with stress can cause sort of an internal cracking or crazing of the plastic. Also, there are some containers, especially if they're going to be storing a fuel, where the requirements are minimal to no residual stresses. So we do have to realize that injection molded parts do have some residual stresses on there, and we'll talk about some of the features of the parts. But we also, for injection molding, we can have waste of the gating system. And in most cases, because the 2 and the 3-plate molds are more common, most injection molding will have some waste. Can you regrind it and recycle it? Yes, and that's very easily done. You might have some, it might degrade a little bit. Most recipes have a maximum amount of reground material, and it's often called regrind because you're just taking the parts and regrinding them. Okay, so now let's kind of talk about some of the features, and I actually probably could have had this in one big list, why I'm saying the process versus the parts, but there is a little bit of overlap. The first is draft is needed, and I think that was a question on the reading assignment. So injection molding needs about 3% draft. Sometimes you can't see it, but this also is why injection molded parts make very good patterns for casting, because they already have the draft. As we've looked, often the gates are visible, or actually it's the location of the gates, not the vision, not the gates themselves. But we can usually see where the gates are. There's likely to be a parting line because we have two molds come together. So the parting line exists and is visible. So oftentimes you do want to try to hide that or incorporate it into the design of the part. So if you can kind of, that's even better. The ejector pins often leave circles. So they often leave marks. I like those because it helps tell me how it was made. Now, these are some of the, well, this is what we have. For a plastic process, we can have fine detail. So that plastic can be moved into nooks and crannies. We can force it. We can get some really nice detail. Complex shapes are possible. And we have good dimensional accuracy. So it is the best for a plastic process. Now, I think we might have talked about this a little bit. Part of dimensional accuracy is uniform elastic deformation or uniform deformation, or related to the amount of deformation. What we see is that when we have a large modulus of elasticity and a large coefficient of thermal expansion, we have less dimensional accuracy. Because plastics expand and contract a lot with temperature, and their modulus is relatively low, so they have a lot of elastic deformation. Plastics in general, we cannot get the dimensional tolerances we can get with metals. That being said, injection molding gives us the best possible dimensional tolerances. So, you know, and if you think about one of the products on the first page was a syringe. We often see medical cups also made by injection molding. That becomes a factor as well. Okay, so we are going to talk about last thing we're going to do is we're going to talk about some variations. These variations can exist in other parts, other processes, but one of the things about plastic is plastics have a low melting temperature, lower than that of metals, lower than that of possibly carpet, and the way the plastic, the way the molecules sort of move and the van der Waals bonds make it such that you can easily mold plastic around something else. So we oftentimes, we have a couple names for this. The most common is insert molding. I don't remember if the video showed it, but this is where we would mold a plastic part around something else, oftentimes a metal. So we could put metal screws, screw threads in a plastic part. That kind of improves the ability for it to hold. We could put a metal needle in a syringe, for example. So we mold the part around, so we mold the syringe around the needle. We could put a conducting copper sheet in a plastic part to make the part conductive because we've got the copper inside the part. The other aspect that we could do is called in-mold decorating. It's been a while since I've seen this in a vehicle, but if you've been in a vehicle and you've seen that they have a carpet in an interesting location, it looks like the carpet is physically attached to the plastic panel, it could be. So we can put a decal or carpet or other things inside the mold and mold around. That's called in-mold decorating. We cannot easily do that with other processes as well. So insert molding and in-mold decorating are variations for plastics, and it's kind of fun, it's kind of cool. So here we have some examples of some insert molding. So here we have the syringe that has, so the syringe has been molded around the decal. I'm sorry, has been molded around the needle. So the needle goes into the mold, the plastic goes around there, and now we have a permanent bond between them. Here we have, in a plastic part, you can sort of see in the corners, we actually have a metal screw thread. Again, these would be put into the mold, then the plastic would be molded around it. This is a part that failed, but you can see the one end, this particular plastic would be surrounding this metal. So this is a part that there was a catastrophic failure during the molding of this, but you do kind of can see the idea. So this would be actually totally engulfed in the plastic part, and it would make that part conductive because plastics are not. Okay. Again, here's an example of a decal. So making of the decal is almost as complicated as the part. So this would go into the mold, and then here is the example of the molded part. So the plastic is totally incorporated into the decal. Here is an older version of that same process. GE Plastics, GE does have a large plastics division. This was one of their kind of products, and you can kind of see on the side, and we can see this in lab next week, how it is just total, it's not like separate that you can pull it off. It's definitely incorporated into the part. Okay. So that is injection molding, and let's see, what do we have? We have a few more minutes. Let's just talk a little bit. We'll just don't want to get too far in, but we can at least start talking for a few minutes about the next processes or additional plastic processes that are generally considered to be thermoplastic processes, and then we'll talk about two processes that are considered to be thermosets. And then I actually have a short video for two of these processes. Okay. So quickly, blow molding. Blow molding and thermoforming are limited to thermoplastics. So we're going to be taking the thermoplastic and deforming it. Rotational molding is one that can do some thermoplastics and some thermosets. Actually, I'm gonna move on to rotational molding because I think that we can do that one fairly quickly. And then on Monday, we'll start with a fun-filled little video on that. So I'm just going to zip ahead to rotational molding. And hopefully I have what I need and want here. So in rotational molding, one of the things you may notice about this particular parts are these are large parts. Now, you know, so for rotational molding, let's kind of consider the size. This one is relatively small. This particular, you know, the first one we see is what I'd call a porta potty. In the video that I have from the company that makes rotational molding equipment or rotomolding, they talk about outdoor furniture and then they show a picture of a porta potty, and I'm always get amused. Here we have a trash bin. So these are very large, like I was going to say canoes and kayaks. So those, if you're ever kind of wondering, well, how do you make those out of plastic? It's going to be rotational molding. A child's play set, and again, this is not a Barbie play set. This is for a small child. So again, large. And then this particular component, if you're like, is that kind of a funky looking foot? It is. This is a smaller product, but it is a low quantity product. It is, if you have imaging equipment, you oftentimes need standards, so you can kind of put the standard into the equipment and then verify it's still functioning. And so this was a part that was made by rotational molding that would be in small quantities that would be for that particular situation. Okay, so I think that why don't we stop here, and on Monday we will look at rotational molding and then blow molding and thermoforming. And again, we kind of think about rotational molding as being very large products. Okay, cool. And again, I will put that review for the exam out on